Hi students, now I am going to explain other topic in sequential circuits and fundamentals. In this module 5th, so we have another flip-flops like master slave or JK flip-flop, D flip-flop and T flip-flops. Let us see first uh, how we can go for master slave flip-flops. Basically, uh, in previous lecture, what I mentioned about the JK flip-flop. What is the purpose of JK flip-flop? Is to avoid the forward condition which was occurred in RS flip-flops. And then, if you see this same JK flip-flop, we know that this is the JK flip-flop. In this JK flip-flop, the all three conditions were same, whereas in SR flip-flop, except that J is equal to 1 and K is equal to 1. What happened for this J is equal to 1 and K is equal to 1? The output gets toggled. So whatever the current present state Q is equal to 0, after applying J, K is equal to 1, you will get a toggle of output Q is turned to 1. And then if Q is equal to 1, initially by applying J, K is equal to 1, then you will get toggle of Q which is equal to 0. Now, what was the problem with this JK flip-flop? If you see this timing diagram for the JK flip-flop, let us take a clock. This is the clock, and J is equal to 1. J is equal to 1. And K is equal to 1, constantly 1. So when we apply this J is equal to 1 and K is equal to 1 in the JK flip-flop, because of this feedback connection in the JK flip-flop, that Q is connected back to this K condition, K NAND gate, and Q bar is connected back to J NAND gate. What happened for J is equal to 1 and K is equal to 1 in this period, in this clock pulse? So when J is equal to 1 and K is equal to 1, you will get the toggle output in this Q. So for example, initially 0, so that output will get 1. When this clock, clock period, the clock pulse time period, propagation delay is more, then what happened? Because of this feedback connection, this toggle output Q output 1 and Q bar is equal to 0 for the application of J is equal to 1 and K is equal to 1. So that this toggled output again feedback to the input, and still the clock was on high. So when still the clock was in high, again that toggle feedback to the input, and that input is passing through this JK flip-flop, like gated JK flip-flop, and that again this 1 becomes 0 and 0 becomes 1. And again still is there any clock pulse is high, again this Q 0 is back to J, this 0 is back to K and 1 is back to J, and which will make that that output race around, around and around and around between 0 and 1, 0 and 1, toggle between 0 and 1 output. So as long as the clock pulse is very long duration, or the height of the clock is very long duration, compared with this JK flip-flop propagation delay, then it's keep on toggle between 0 and 1, 0 and 1 until it will reach to clock low, until the clock gets low. So likewise, so we will get this unnecessary race around condition happened in the JK flip-flop. So this drawback will be eliminated by another JK flip-flop, which is called master-slave flip-flop. Which is one. This master-slave flip-flop is the famous JK flip-flop to avoid the race around condition. So this is actually constant, and then again because of this clock pulse, again it is race around and still constant, and then it will gives the race around condition. So this race around condition eliminated by providing the extra JK flip-flop, gated JK flip-flop, following which this the basic JK flip-flop. So eliminate this connection and providing another JK flip-flop, and this feedback is extended to last queue, like this extended to this one extended to last Q bar, and this Q is extended to this K. So let us see that what is the how can we provide these two different kinds of gated JK flip-flop, make them to control this, avoiding this race around condition which was in master step flip-flop. This is the diagram. We can see here there are two different JK gated JK gated SR flip-flop are called JK flip-flops. One JK flip-flop will be treated as master latch or master JK flip-flop, and the second part following which of this master is called the slave JK flip-flop. So the only difference is that the feedback connection is extended for the last slave JK flip-flop. So this slave JK flip-flop Q bar is connected back to J input, J NAND gate input, and this Q slave Q is connected back to J input. That is one extra connection. And the second one is the clock input is connected to master JK flip-flop, and this clock is connected through some inverter and connected to the second JK flip-flop like a slave flip-flop, so that we can control this race around condition. This is actually connection of a master slave JK flip-flop. There are two parts. One is master, act as a master, another one is slave. And now let us see that operation. So in this master slave flip-flop also there was no problem with that all three cases, like J is equal to 0, 0, K is equal to 0, and J0, K1 and J1, K0. Only the problem was that both inputs were 1. So how to avoid this race around condition? By providing these two kinds of flip-flops. One act as a master and another one act as a slave. The input signals, which are called J and K, are connected to the gated master SR flip-flop, which locks the input condition while the clock input is high. Or in other words, as long as the clock input is high, which locks the logic value of the output, toggle value of the output of the master. And then some other time, which means that when clock is low, that a slave becomes active, and then which will locks the logic after that and following up clock of high. If you see the condition, for example, when as we can see this master slave operation, master slave diagram. Suppose J is equal to 1, K is equal to 1, and we'll get we remember that the clock pulse is a edge triggered. For a positive edge trigger of the clock, the master JK flip-flop is enabled and master JK flip-flop is active, and which allows the signal. And then whenever again reach back to the positive edge until this again second positive edge, the output kept constant, like kept unchanged, which can stores the logic value in the master. Whereas in the sim, we can connect some inverter for the slave. So in this slave, it is just complement that slave clock. Whenever clock is low, the slave is connected, because in the master is when negative edge means the slave is complement means slave is positive edge. So in this negative cycle, the negative edge slave is active, the positive edge master is active. Again, next to negative edge, the only the slave is active. Remember it. So now when j is equal to 1, k is equal to 1, and the clock is positive edge during cycle, when clock is positive edge, then you will get the master output QM until this time. Master holds the logic QM, whatever it is, toggle of current state. For example, current state is 0, that a complement of like toggle of that current state 0 to 1 in the QM. During this negative cycle of the clock, the slave is active. The slave which gives the Q toggle output of Q. Okay. So J is equal to 1, K is equal to 1. Let us take QM is equal to, for example, master flip flop output is 0. When master flip flop output is 0 here, which means when output is 0, so and also initially we assume that the Q is equal to, for example, let us take this one. What is the actual, we assume that initially that entire master slave JK flip flop is initially the output is 0. What does it mean this output is 0? Means this one is 0 and Q bar is equal to 1. That Q bar is equal to 1 means here it is 1. So when clock is positive edge triggered, immediately triggers the master's flip flop. That means we have a 0 here as we assume, and k is equal to 1. So k is equal to 1, 0 and clock is high, then this NAND gate is 1. Because of NAND gate is enabled with this one input is 0, then output automatically 1. So then here this feedback input is 1, j is equal to 1, clock is high, will get 0. This 0, 1 inputs make the QM, so automatically this NAND gate gets 1 and this NAND gets 0. Because why this NAND gate 1 means initially one input is 0, that NAND gates will immediately respond, then output is 1, that 1 is appear here, 1 into 1 complement is nothing but 0. So now this 1 and during this is happened in this positive edge cycle and holds the same output, this one master 1 output during this clock. Now 1 is there in the QM and 0 is there in the QM bar. What happened is during the entire cycle, this entire cycle, the slave is in not active. The slave was in not active because it's a clock bar. So when clock is positive edge and hold the clock, at the same time it will give the negative edge cycle, negative edge in the clock bar, so that the entire slave was in inactive mode. So what happened when this during this negative cycle, during this negative edge, now slave is enabled. When the slave flip flop is enabled, we have already 1 and 0 in the output QM, 1 in the QM and 0 in the QM bar. During the negative cycle, negative edge cycle, that slave is enabled and this 1 and 0 passing through the slave flip flop, then immediately this one is 1, because one input is 0 in the NAND gate. This one is 0, and which makes this 0 makes this NAND gate 1, and this one is available here 1 into 1 complement nothing but 0. What does it mean? Initially we assume that Q is equal to 0. After applying this clock positive edge and then negative edge, we will achieve toggle output. The same output which was occurred in the JK flip-flop. The only difference we have to observe, it is to be noted that, okay, now this toggle output, because of feedback connection, if during the negative cycle you will get this toggle output, but what happened, this during the negative cycle, this feedback, even though the feedback connection go back to primary input of the master slave flip-flop, which will not make the master gets enabled and that output passing through the master. So it won't allow, because during the negative cycle we will get the toggle output of the slave, but this output won't enable the master because master is inactive. This during this negative cycle master is inactive, even since since then again get back to positive edge of the cycle. So during this time it never happened of this race around condition. So once reaching this 1 and 0 in the output, that will get back to input, but clock is low, then it won't allow to that feedback connection to the master flip-flop. So in this way we can stop the race around condition. We can't we can't allow that race around condition. So this is the one of the advantage in the master slave flip-flop. So it's a same operation happened in this master slave flip-flop which was occurred in the JK flip-flop, but we can protect this race around condition. When we see this timing diagram for master slave flip-flop, what happened in this master output and slave output, when the clock is high during positive edge, the QM, for example QM get 1, again that it holds the output of 1, logic 1, till again it reached positive edge cycle, next to positive edge of the cycle. What happened in the slave output, when the clock is positive edge and maintain the logic 1, and then when it reaches to negative edge, immediately clock bar is active. So clock bar means a complement, when negative edge means complement is positive edge, when then slave is enabled. At that time the Q is which holds the output 1. So this holds the output 1 until again it it get back to the negative edge cycle. So slave holds during this period to this one, master holds this time. So when it is positive edge, it changes the state and holds the same state, and again it changes the state until it reaches to positive edge cycle. Similarly, clock in the negative edge change the state and hold the same output until it reaches to negative edge of the next clock, negative edge clock. In this way there will be no chance of getting race around condition. The toggling takes place during the whole process, since the output changing once in a cycle. Next, move to D flip-flop. What is D flip-flop? It is nothing but delay flip-flop, and how it came to picture. When we see that a SR flip-flop, one of the main disadvantages of the basic SR NAND flip-flop is that the intermediate input condition of S is equal to 0 and reset is equal to 0 is forbidden. So this state will force both outputs to be at logic 1 in the SR NAND flip-flop. Right now. So this unavoidable or forbidden condition of the SR flip-flop when both S is equal to 0 and R is equal to 0 then eliminated by the D flip-flop, delay flip-flop by providing just extra one inverter diagram at the input. This D flip-flop is also called data latch or delay flip-flop or D-type flip-flop. This D flip-flop makes this S and R inputs become complement of each other, which ensures that the two inputs S and R never equal to 0 or 1 to each other at the same time, allowing us to control the toggle action of the flip-flop using one single D input. Let us see how it connected to avoid this equal inputs occur, which causes the forbidden condition in the same outputs occur in the SR flip-flop output. If you see this diagram, this is the simple gated SR flip-flop in the which is represented in the dotted shaded region, and we provide extra inverter connected between main D input to the R. So when we provide the inverter to R input, so that we will avoid this chance of getting the same commonly same outputs appear across the output. So when we joining this S and R with the inverter connected between D input and R, then which will become as a D flip-flop. What happened by connecting this one? When I am giving 0 at the D input, the directly 0 positive S input and its complement 1 is go to R. When I am giving 1 here, when I am giving 1, directly S is go to 1 and complement 0 is go to R. So there will be no chance of same common input to S and R, either 0 or 1, which will make that output comes under forbidden case. So this unavoidable condition can be eliminated by this D flip-flop. Let us see that the operation and truth table for this D flip-flop. What happened when D is equal to 0? So D flip-flops are used as a part of memory elements and data processing as well. The major applications of D flip-flops are to reduce delay in timing. If you want to get delayed by 5 seconds, each D flip-flop produce 1 second, then you can provide 5 D flip-flops for in series, then you will achieve you can get that 5 times delay by providing 5 D flip-flops, so that it can be used as a delay in timing and used as a buffer. If you use whenever all the times in the digital circuits, whenever buffers are there, which makes from D flip-flop most of the time, and sampling data at specific interval. This is the simple truth table. In this truth table, when clock is low, irrespective of D input, the present state it's the next state is a complement. And when clock is high, when D is 0, what does it mean? D 0 means S is 0 and its complement of the R is equal to 1. When S is 0, R 1 means in the diagram. When D is 0, S is 0, R 1. When S is 0, R 1 means immediately we comes under SR flip-flop. S is 0, R 0, R 1, which is nothing but reset. of the output. What does it mean? Reset of the output means Q is equal to 0. When S is equal to 1, like D is equal to 1 and S is equal to 1, R is 0 means a set, which means whatever the present state, it will change to 1. That will happen in the D flip-flop. So when clock is high, D is 0, which means reset of the output, then output will be 0 and it's a Q bar, like Q bar output, complement output automatically 1. And when clock is high, data is 1, which will make the set of the output, whatever irrespective of input. If it is current state is 0, which will come converted to like turn to 1. If it is already there in the current state 1, the same will maintain the same 1, so that we can get the set output in the Q. Its complement is 0. So simply, if you observe these two columns, whatever the data input D is given, same output passes through the gates. If I am giving D input 0, you will get the same 0 output across the output. If I am giving 1, the same output 1 will be appear across the Q. What this means, data transfer are delayed. So the same 0 is passing through the output by consuming of 1 seconds, by consuming of 2 seconds or 0.5 seconds. So which passes the same logic value by consuming some time by application of clock high. So that's why it is called delay flip-flop. These are the different conditions, different cases in the D flip-flop. D is equal to 1 when clock is 0. We'll get the unchanged condition, no change condition. D is equal to 1, clock 1. It means that set of the output. And when D 0, it's the clock, whenever clock is 0, automatically S0, S1, 1, R1, there will be no change in the output. Likewise, when D is equal to 1, clock is 1, indirect, which means S is the S1, R0, which is equal to Q is equal to 1 and Q bar is equal to 0. Actually. This one. Therefore, the mathematical equation, like characteristic equation. Let us see that characteristic equation. How many inputs are there? D and the present state Q, Qt. And what is the next state? Qt plus 1, for example. Or Qt plus 1 or Q. Next step. When D is equal to 0, if present state 0, next state is also 0. When D is equal to 1, present state is 0. Sorry. When D is 0, present state is 1, next state is also 1. When D is 1, which make this set in the output. When initially, if it is 0, initially, the output is 1. When D is equal to 1, initially that present state is 1, initially the output is 1, next state is also 1. So how can we get this characteristic? This is the characteristic table. This table, from this characteristics table, we will get a characteristic equation. If you take the K-map, here we have only two variable K-map because two inputs D and Q present state Qt. So we want to get this Qt plus 1 equation. This is for Qt plus 1 equation. We have a D and Qt inputs. So when D 0, Q 0, 0, 0. When D 0, Q 0, where is the one logic one? D1 Q 0. D1 Q 0 logic 1 we need to provide, and D1 Q1. Where is the D1 Q1? This is the D1 Q. So we can make the pair. So what is the Boolean function for this qt plus 1. Qt plus 1 is equal to, this is the, which covers the two columns, so cancelling of these two columns, and only we can consider this row, which is nothing but d. So qt plus 1 is nothing but d. So next always means whatever the d input, same appear across the next step, which means q is equal to qt plus 1 is equal to d. That's why it's called delay flip-flop or a data transfer flip-flop. Next we will see that T flip-flop. T flip-flop. This is very simple. By connecting the J and K joined together will make the T flip-flop. We have a JK flip-flop. Simply if there is no joining of J and K, it is nothing but JK flip-flop. If I am joining this J and K, it is nothing but T flip-flop. Like no, the T flip-flop is simply, like it is a simplified version of JK flip-flop, which is obtained by connecting the same input T to both the inputs of J and K of the JK flip-flops. So when we joining together, what happened? When joining together, what happened? So we have a J and K, or these possibilities. So when we joining together, there are only toggling possibilities like 0 and 1. So when we not 0 1, these two cases, avoid this 0 and 1. So when we joining together, T is equal to J, T nothing but J equal to K. So when T 0 means indirectly J0 K0. What happened in the J0 K0 no change condition? When T is equal to 1, J1 K1 means toggle condition. Okay. So we have only two options. When 0 T0 unchanged, T is equal to 1, you get toggle output. This is happened for positive clock transition or negative clock transition. So if you see this truth table, whenever T0, present state is 0, the next state is also 0, unchanged condition. As long as T0, whatever the present state, whether it is 0 or 1, if it is in second case 0, 1, then the next state is also 1. But whereas in T is equal to 1, that present state toggle to next state, present state toggle to next state. So if you see the characteristic equation, like characteristic table, okay, present state is 0, next state is 0, next state is 0 when T is 0. Okay, when T is 0, we can actually this T is on left side. When T is 1, if present state is 0, next state is 1. When T is 1, present state is 1, next state is 0. When T is 0, present state is 1, next state is also 1. So if we see this table in the K map, the output of the T flip-flop always toggles for every positive transition of the clock signal when T remains at logic high. Hence, T flip-flop can be used as in a counters. As long as the clock changes, transition of the clock, that a T values, like change its toggling output. So based on this series of connections of T flip-flops, we can change the states and the counters by changing the toggle of output. So now consider the K map. Here also two variable K map. One is T and the present state Q to make the equation for T n plus 1 or T plus 1. Okay. So T0, 0 and 1, 0 and 1. T0, Q0, no output. Next state is 0. And T0, present state is 1. Next state is also 1. Make this one. And T1, present state is 1. T1, present state is 1. Output is 0. No need to consider. T0, make this one here T 0 1 1 0. What is where is the output? Next set two ones are there. 0 1 case, 1 0 case. So T 1 0 1 no, T 0 1. So we can have single circles because no quad, no pair. So that means we'll get a, for this circle we can have T bar Q like this one, second term, and for this circle T and Q bar. This is 0, which means Q bar. So T Q bar, which is indirectly means a simply OR gate, XOR gate, T exclusive OR gate with the present state of output, which is nothing but Qn plus 1. Next step in the T flip flop. So likewise, this T flip flop always toggle for every positive transition of a clock signal. So when we connected this together, which make use of as a counters in the sequential circuits. Likewise, these are all flip flops. By considering the truth table, like circuit diagram and truth table and characteristic equation, characteristic table and characteristic equation, we we try to understand of these all flip flops. So each flip flop which will make use of different applications. When we consider that a simple SR flip flops is a basic foundation flip flop, and then JK flip flop. Most probably we can prefer that in the counters, synchronous or asynchronous counters, we can use this JK flip flop and T flip flop, and most of the time we can use the D flip flop as a delay or buffer. We can make use of all these different flip flops. So these different kinds of flip flops will helps to understand, make use of these flip flops to design this further sequential circuits. If you want to implement, if you want to implement the shift register, if you want to implement counters, if you want to implement any sequential circuits, we make use of this basic flip flops because the flip flop is a basic element to store the logic one, and it will act as a memory element. So it's in every sequential circuit you must have this kind of element, this kind of block, like the memory element, which will make from different kinds of flip flops. So likewise, with the help of this basic flip flops, then we can go with the further sequential circuits. But finally, remember that sequential circuits made with the combination plus memory element, and the basic fundamental component for this memory is nothing but latch. And by providing a controllable latch with the gated inputs, which is called nothing but flip flop. So the basic difference between the latch and flip flop is without clock is nothing but latch, and by providing the clock pulse with a gated input, which is nothing but flip flop, which can store the binary information of either 0 or 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.